So we're now on to page 10 of our booklet, and we come to a little subheading that says prescribed practical question. Something we'll talk about a wee bit more when we get back to school is the fact that you've got a practical module at the end of year 12, which involves sitting or doing a practical experiment in the lab and also sitting a practical theory exam in the exam hall. With the practical theory paper, you can often get questions like this. The example you're seeing on this page, where you're given a description of an experiment. So this one's about the reactivity series, because it's in this topic. And you're given some questions and you need to evaluate the results and talk about being a fair test and things like that. I'm not going to go through the answers of this now, just because I don't want the videos to be too long, but do feel free to have a go at this. It's good practice and gives you an idea of the kind of style of question that could come up in that practical exam. But obviously we'll talk more about it when we get back to school. So keeping on with the content then, so on page 12 we come back to we're almost at the end, last couple of little subheadings. This bit's on the extraction of metals. And it's more about where we get metals from in the world around us. Because if I just take an example, if you look at this pen lid, as lots of pen lids have, it's got a wee clip here, it's made of metal. I'd say probably it's aluminium, it's quite flexible, quite lightweight. The question now is, well, where did this aluminium come from, or where does any metal come from? Because you may have in your head an idea that metals are just dug up from the ground and you just find lumps of iron, lumps of aluminium, etc. You don't actually find that. With some really unreactive metals like gold or silver, the really expensive ones, you do find them as lumps in the ground. But for most other metals, because they are reactive, you'll find them in the ground after they've already reacted. In other words, if I took a lump of iron and planted it in the garden, it would very quickly react with the oxygen in the air to make iron oxide. So one type of iron oxide is Fe2O3. Now, that's what you find in the ground when you're trying to get iron. This is what we call an ore. So whenever you see like iron mines around the world, they're really digging up this iron oxide rather than iron itself. So an ore is just a rock that contains that metal compound you're looking for. So if we say we're trying to get iron, we want to get it back from the iron ore, the iron oxide. We need some way of doing that. We need a way of turning it back into iron so we can use it for buildings and things like that. This is known as the extraction of metals. You're extracting, so you're taking them out of a compound that they're found in naturally. So this is how we go about doing it. So some unreactive metals are found in the natural state. So say gold, you actually can find just as lumps in the ground. Though often metals are found as metal oxides known as ores, and that's just because they're quite reactive. Even if they were metals at the start, very quickly they're going to react with oxygen around them and turn into the metal oxide, which is the ore. The little definition of what an ore is, I think this has come up in the exam before. It's a rock that contains a metal compound from which the metal can be extracted. So you dig up rocks out of the ground and you're trying to get the metal from those rocks. To extract the metal, you must remove the oxygen from the metal oxide. This is called reduction. We'll come to that word reduction a wee bit later. So to give you an idea, so I'll change the metal just to keep it, show you a different example. So let's say I had copper oxide. What I'm basically trying to do to get copper is to get the copper by itself and to get the oxygen separate from it. So that's the process I'm trying to do here. I'm trying to split apart the oxygen and the copper to get the copper for myself. In terms of how you do that, like what actually takes the oxygen away, you got two options here. Well, one thing you might be thinking of at the minute is, hold on, you can just do a displacement reaction. You get more reactive metal and that would push out the less reactive metal, which you want. That would actually work, but then if you think about it, you're having to use very expensive reactive metals like potassium to displace other like less reactive metals. It's not very economical. That's why we don't use displacement reactions with metals to get to work. The first one method we use is electrolysis. Now I don't want to go into too much detail here because it's a topic of itself later on this year. It's basically using electricity to split a power compound. So if you had electrolysis of copper oxide, you put two electrodes in copper oxide. At one electrode you get copper and one electrode you get oxygen, and you can collect the copper there. The second method we use is called reduction using carbon. Now this sounds a wee bit strange. Carbon basically is like a metal in that it kind of takes part in displacement reactions. What I mean is this, so if we look at the little equation, if I take copper oxide and react it with carbon, so literally just like charcoal, is pure carbon, what the carbon is able to do, because it's actually slightly more reactive than copper, is it's able to displace the copper from copper oxide, and that will leave you with copper itself and carbon dioxide, which, as you know, is kind of like a common stable compound. It's balancing like this. So looking at, I know this does look a bit strange because I'm kind of saying it's a displacement reaction, but carbon's not a metal, but it does work like a metal in this case. Carbon's more reactive than copper, so it can do a displacement reaction, which involves taking the oxygen away from the copper, leaving it by itself, and that's what we want to happen. CO2 gets lost as a gas, job done, and we get the copper by itself at the end of the reaction. So that's how we extract it. So those are two methods. You might think, well, what have we got two? How do we know which one to pick? It depends on how reactive they are. So that's what's written down the bottom here. And this is kind of important, you know where the dividing line is. Heating with carbon to get metal ore back into metal only works for the least reactive metals. Because if we were trying to show our reactivity series, we would put carbon in here. Carbon's more reactive than zinc, iron and copper. It's less reactive than aluminium up. So we can't displace any of these metals with carbon, only these three. Once you go above that, we have to use electrolysis. Electrolysis is a wee bit more expensive because it uses a lot of electricity, so that's why we use the carbon for these three, if we can. But beyond carbon's reactivity, we have to use electricity to get the metals separated. So it's a little bit confusing, but there's not actually too much detail on this page to know on this page. Essentially, if you got the idea that we want to get metals, they're not found naturally underground, they're found in oxides because they've already reacted. We're trying to find ways of getting the oxides back into the metals, so the oxides called the ore back into pure metal. We've got two methods for doing that. If it's really unreactive, we can use carbon because carbon takes oxygen away to make carbon dioxide. But if it's quite reactive, we have to use electricity, and I'm giving you no details about that at the minute because it's a topic in itself later on. Just know it's called electrolysis. We use it for the reactive metals to get them back from their ores.